Hello everyone, welcome to Sergio Prado's YouTube channel. So in this video, we will learn a little bit about how to use containers on embedded Linux devices. So I'm gonna cover a little bit about what a container is, how to use containers, why to use containers, when, and everything in the middle. So closer to the end of the video, we will also run Doom in the device inside the container. So try to follow the video until the end so you can learn how you can run Doom on any device with a container. So yeah, let's get started. Before I open my terminal, I want to talk a little bit about what a container is and what are the motivations behind using containers, especially on embedded devices. So first of all, what a container is. A container is a way to package software. There's a very important concept to understand. A container is not a virtual machine. A container is basically, as I mentioned, a way to package software and all of its dependencies in a very standard, deployable, runnable form. They have a number of resources allocated to them, like CPU, memory, I/O, networking, and they run isolated from the rest of the system. So it's not a virtual machine. It's just a mechanism to package and run software. For example, if you are a Fedora user, you are running a container. You are running containers because you are probably using Flatpaks. They are packages that are deployed and run inside containers or using containers technology. Also, if you are a Ubuntu user, you are probably using containers as well, even though you might say I don't use Docker or something like this, because snaps, another kind of packaging mechanism from Canonical, they are also containers. They use container technologies. So this is a very important concept to understand because sometimes people say, I will not use containers because I don't want to have processing power issues. I mean, I don't want to consume too much CPU. I don't have enough CPU. I don't have enough resources. And most of the times that is not true. Process running inside a container will not use more CPU. It's not being emulated somehow. It's just running natively in the system. So that's very important to understand. It is just isolated. So it runs isolated from the rest of the system. It cannot see other process. You cannot see like other mount points, other users. So there is a feature in the Linux kernel called namespaces. That's one of the main features that makes it possible for you to run isolated applications in the system. And a container engine, the software responsible for running containers, uses that and other kernel features to run software inside a container. So that's the main idea here. It's pretty much different from a virtual machine because it's much lighter. It shares the kernel. It runs natively in the system. It is not emulated or virtualized. That's very important to understand. Now, you might also ask why I would use containers. So the first main reason would be productivity. You just want to focus on application development. All right, but why is that? When we work with embedded Linux, we usually have to care a lot about the Linux distribution that we are using. So we have to work with a build system like Yocto, Open Embedded, Build Root to build and maintain our Linux distribution. And this is usually a pain, especially for users that are not used to do that. Let's say, for example, you want a web developer to work on embedded Linux, or a mobile developer, or even people that are used to write software for microcontrollers. They know nothing about running BitBake, for example. And it's a kind of, they get frustrated, right? When they want to build a product with embedded Linux, but they first need to learn and understand all of these different tools and technologies to build the infrastructure, right? The distribution, tool chain, that stuff, to write their applications. So if you use containers, you can forget about all of that, right? So using containers, the development time is reduced because you can focus on application. You don't have to care much about the infrastructure to run the application because you're gonna ship this infrastructure inside your container image. That's one of the main ideas. It's very easy to extend the distribution with anything you want, right? So you just need a recent kernel with a container runtime, like Docker, Podman, or any other container runtime. And then you can run any container on top of it. We're going to see in the examples in a few minutes how easy it is like to run a web application on embedded Linux. Compared, for example, to building a Linux distribution with a web server. So you really can reduce development time if you decide to use containers. Another advantage is, I would say, it's flexibility. It's very easy to use any tool you want, programming languages, runtimes, any other technology. Like, I mean, you can mix anything you want in the system. Let's say you want to run a Python 2 application and also a Python 3 application. You can. Because you can have a container with Python 2 and a container with Python 3. If you try to mix everything inside the base distribution, that might be a problem. So you can have a container running .NET application, a container running Python, a container running native code. You can mix, for example, libraries. Let's say, for example, you have an application that needs an old version of a library. But that old version of that library, it's incompatible with your base operating system. Of course, there are always ways to solve this issue, but it's much easier with a container. You can just create a containerized application with that library inside of it and ship that container and run it in the device. So it's much easier to manage the system. You have much more flexibility. If you have a Python developer, you don't need to care about creating a distribution with Python inside of it. You just say to the developer, okay, just create a container with Python and run in the device. Problem solved. If you have a device in the field, let's say, for example, you ship a device without Python, and then later on you decided to use and run Python applications. Without containers, you will need to update your base operating system, right? To ship a new version with Python, so you can run a Python applications on top of it. Now, if you just have a container engine, you don't have to update the base distribution. You can just run a container with anything you want. So it's really, really much more flexible. Another advantage is portability. That means if you create a container for a specific target architecture, you can run that container anywhere compatible with that architecture. So if you create a container for ARM 64 bits, you can usually run that container on any ARM 64-bit architecture. That means you can share a container image with different devices that have the same CPU architecture. And this is very nice. Another advantage is modularity. I think containers kind of motivate the development of a more modular system. And that, of course, improves maintenance, improves portability, reuse of stuff. That's mainly because you can break down the problem that you're trying to solve in multiple containers, right? You can have one container with a database, one container with a web UI, another container with some kind of system level applications. And then you can reuse that anywhere. Containers make it easier to control resource usage, and that's very nice. So with containers, you can control how much CPU you want to allocate to a container. You can control how much memory you want to allocate to a container, and so on. And that's also very nice. Of course, you can do that without containers, but it's easier to do that with a container engine. Another interesting advantage is updatability. So it's really easy to update containerized application. Because you can just pull new container images while you are running the old versions. Switching an application from one version to another is a matter of stopping a container and starting a new container. You have by default Delta updates with containers. You design well the layers of the containers. So when you update a container, only the updated layers will be pulled from the container registry. So you really can leverage that, right, in an embedded Linux device. Last but not least, security. It's important to understand that a container is not secure by default, but it provides you the infrastructure to build a more secure solution. If you are interested about this topic, security on containers, I have a talk about this. You can search on my channel for this talk, 1 hour about how to secure containerized applications with a focus on embedded Linux. So those are a few kind of advantages that I see to use containers on embedded Linux. It's important to understand the disadvantages, right? As I mentioned, a containerized application will not use more CPU. That's very important to understand. But of course, it will use a little bit more resources. One of those resources is storage, because you have to store the container images, and each container image has its own set of libraries with dependencies, so you might duplicate stuff. That's the cost, right? There are some optimizations on that. The layering mechanism from Docker really helps with the way we manage like the layers, and it really improves the usage of storage. But this is a cost. There is some cost that start up, right? Because starting up a containerized application takes more time than starting up native application. That's another cost. But as soon as it is running, it will not run slower. Okay, so you can be safe on that. And also, there is no impact on, let's say, like real time, for example. If I worry about real time events, so you can really design real time applications if you want, run inside containers. I don't see any issue with that. The challenges are the same. That's what I mean. Running inside or outside containers, you have the same challenges for designing real-time systems with Linux. So those are a few of the trade-offs, let's say, right? But I usually say, like, if you have enough resources, why not? So if you have enough resources, like enough storage, CPU, and memory, why not run applications inside containers and leverage all of those advantages that I mentioned? So that would be one of the reasons to use containers. I have enough resources. I want to be more productive at the application development. Another reason would be I want to mix different technologies in my system, and I don't want to care about conflicting technologies. Like if I enable this, then I might have problems with that. Since you are running applications isolated from each other, you can use any technology on any of the containers. Another reason would be I want to use different runtime environments. Like I have my applications built with .NET, and then I want to, but one application needs one version of .NET, another application needs another version of .NET. Then why not having two containers? Um, it it could be harder to have two runtimes in the same base system, but with containers it's much easier to do it and manage that over time. Another motivation would be security. So you want a more secure system. You want to run applications isolated from the rest of the system. One way to do this is containerizing the applications. And last but not least, as I mentioned, you might want to use containers because you want an easy way to update the applications remotely. Now, another question is how to use containers. So now it's the time. I'm gonna show my terminal and we're gonna play a little bit here with Embedded Linux and run containers on it. All right, so what you can see here is my terminal. So here I'm running BeaglePlay. CPU. It's BeaglePlay, as you can see here from my camera. And I built a small Linux system with build root. And I have Docker here. Yes. So I build a system with Docker. Before running a few containers here, let's talk about how to build a system with support for containerized applications. So the first thing is you need to build the kernel with support for, with some features enabled to make it possible to run a container engine, the software that will manage containers in the system, like Docker. There are a lot of different features that need to enable. One option here is to just run this script. So this script, checkconfig, is a script from the Moby project. The Moby project is one of the projects from the Docker community. And here inside the contrib, we have this checkconfig script. It will basically look at your kernel configuration and let you know the features that you have enabled or disabled related to Docker. Make it possible for Docker to run in our system. I have it here already. I already downloaded. It's just a shell script. And I'm going to run it so you can see what happens. Check config. It basically, let me go to the beginning here. So it reads my kernel configuration from proc config gz, and then it tells me the configurations that I have enabled are disabled. So here we can see that I enabled almost everything before the video. And of course, you might want to look at this missing options. Some of them might be important, but in my specific case here, almost everything is enabled. If you go to the beginning, you can see like the general necessary features. Those features here, you might probably want to enable all of them. Those are kind of the features used by container engines to manage containers, like namespace, cgroups, some networking features. There are also optional features. You can run a container engine without it, but you might probably want to have a look and enable most of them. It depends on your use case. So that's one of the important things. Make sure your kernel is able to run containers. And one of the ways to do this is running this checkconfig script from the Moby project. Now, of course, another thing you have to do is to enable a container engine. Um, there are a few container engines out there. Docker is one of them, one of the most popular, and that's what actually I'm running here. So I'm using build root. If I run here, make menu config in build root, and then search for Docker CLI, I can see here I have it enabled. Docker CLI, that's the command line tool from Docker, and also Docker Engine, that's the Docker daemon. And there are a few other software that will be enabled as dependencies, like runc, for example, Containerd, that they are all used together to run container in the device. It's harder, and it's not harder, but it is more work to enable the features in the kernel than to go here and just enable Docker in the system. You can do the same thing in Yocto, but with Yocto, you would need to use a layer called meta virtualization, and then enable a few packages, add a few packages to your image. Basically Docker and Containerd. Don't remember actually everything that you need to enable, but that would be the same process. All right, and now I have Docker here running on my system. Docker info will show me information about Docker engine, and I'm now able to run Docker. So I don't pretend here to teach you how to use Docker in detail. I don't want to extend much this video, but I want to show a few things. So for example, you can run containers with Docker run. The first container that you would probably want to run is the hello world container. This container will basically print a message to you, just to show you it is working. Everything is working. So when you run a container, what Docker does is it search for the container in your device. It cannot find the container. It will go to the repository of containers. That's what we call it, a registry. And the default registry is Docker Hub. It goes there, pulls the container image to your device, and then run the container. As you can see here, this output is from the container. I can run here Docker images to see. Actually, I have a few images here, right? I'm gonna prune everything. Docker prune system prune -a-f. Those are from my previous test. So removing everything. Let me run in again just to show you that we're gonna have just one Docker image here. So the container is very small, that's why it pulls very fast. All right, so I can run here Docker images, and then you can see we have just one image, hello world, that we executed here. That's not very useful. Let's do something more useful. Let's run a web server. So Docker Hub is a kind of a marketplace of applications, let's say. So you can run anything you want that you have here. For example, let's say you want to run a web server. Let's search here for the Nginx web server, a very popular web server. There is a container with Nginx. You can just run it. So you don't need to care about creating a Linux distribution with Nginx and building it, and after a few hours, you might want to test it. We can just run a web server in a few minutes here. So let's do this. I already have the command here because I don't want to type everything. So let me take here this one, and then I'm gonna run the command, and as Docker is pulling the image, I'm gonna explain how it works. So I'm running here the Nginx container, right? Since there is no Nginx image in my device, Docker will pull this image from the registry. So actually, it already pulled the image. Now it is extracting. This is the command that I'm using to run the container. Let me explain you what this command does. So Docker run to run containers, -d to run it in the background, because by default it will lock my terminal and then the container will run. I want to get back my terminal and then it will run in the background. It's similar to running with the ampersand symbol in Bash. Then I'm naming the container with web server, just because I want to reference this container with this name, web server. I'm also mapping a port. So when you run a container, the network inside the container is separated, isolated from the network outside the container. Since this is a web server, and this web server is exposing me a TCP port, I cannot really access it. So I have to explicitly map the port to the host OS. That's what I'm doing here. So I'm mapping the 80 port from the container to the 80 port in my host OS. So if I access the port 80 from my device, I will get into the port 80 inside the container. Just a port mapping configuration. And then we have the name of the container, nginx, and then the tag. The tag is just a way to differentiate different versions of that container. People usually use the version of the software in the tag, but you can use actually anything, any string. All right, I guess it finished it. So now it will run the container. As soon as you get the terminal, that means the container is running. Created the container. This is the hash from the running container. And now I have back the console. That means the container is running. So if I run here docker ps to list the container that is running the system, I can see nginx is running here for 11 seconds. Let's test this container. So what is the IP address of the device? It's this one. All right. It is running. Welcome to nginx. How long did it take to run a web server in the device? 2 minutes. It would take much, much more time to do this, for example, with the Octo or even build root. Because you have to change the configuration of the base operating system, and then you have to rebuild it, and then flash the device, and then reboot it. And then maybe a few hours later, you have the web server running. Much faster. That's what I meant about like productivity, right? You can run anything. Do you want to run a database server? All right, Docker run, and then you can run any database server, any web server, any kind of software that is packaged, that can be packaged inside a container. Let's now do another test. So I have here, let me just quickly show you a few Docker commands. So as you can see here, now we have 2 Docker images, right? And then we have 1 container running. It's important to differentiate between images and containers because images, they are templates. Containers are instances of this template. So when you run a container with Docker run, it will take an image and run it. I can even run multiple instances of a container image if I want. Docker images show you the images, right? And Docker container show you the containers. This command here is basically the same as docker ps. I can stop and start. I can list process inside the container, docker top, and then the name of the container that I use, web server. So here you can see those are the processes running inside the container. It's 5 processes, right? Actually, if you run PS on your base operating system, you can see the same processes. As I mentioned, you are not virtualizing anything here. the process I running natively in the system. The only difference is that they are running isolated. They cannot see other process. They cannot see other mount points from the file system. So they are isolated. But they are running. They are there. I can even like get inside the container if I have a shell inside the container. So let me show you here. This is my base operating system that I built with build-root, as you can see. Then I can docker exec inside the container. I can say I want to run a command interactively with IT inside the web server, and I want to run bin sh. Now I'm inside the container. As you can see, it's the Debian container. So that Nginx container actually is built on top of Debian. I can try to run PS here, but there is no PS command inside this container. But I mean, I can install PS, so I can do like apt update, apt update. This is an inception of systems, right? Because I'm running a system inside of a system. That's kind of what you can do with containers. I have a Debian system running on my small embedded Linux system. apt install proc ps. So now I'm installing the proc ps package that has the PS software because I want to run PS in my container. And now I can run PS aux. We can see all of the processes running inside the container. You can see here that Nginx has the process ID 1, right? Because it's the first processes running this system. It's not the init manager, but it's the first process. There are a few childs, and then here you can see my shell. Very nice. Then I can exit the container. Can show you again here. I'm back to build-root. The container is still running. I can stop it. Docker stop. Web server. And then I can stop the container. Now if I go to my web page, I cannot access it anymore. I can manage it as an application. I can start it again. And then it's back. Very nice. Let me show another example. So I have here a web application. Actually, it's not a web application. I mean, it's just a HTML file with a CGI script to blink LEDs. So let me show you here what I have. This is my HTML file, very complex. It just show a message, BeaglePlay web interface, and then it shows 2 buttons for you to blink the LED. I also have the CGI script that will be called when I click on the buttons. So it's a shell script that, depending on the information that web server will pass to me, I will turn the LED on or off. I also have a lighttpd configuration file because here I'm building a container with the lighttpd web server. And I have here a Docker file. So a Docker file is a file to build containers, Docker containers. This is the content of this Docker file. Again, I don't pretend to teach you how to write Docker files. I just want to quickly explain what I have here so you understand the concepts. So this is the file that has the logic, right, to build a container. When you build a container, you always build from another container. I mean, you can build something from scratch, but that's not really common, but you can. Here I'm building from the Alpine container. Alpine is a very popular Linux distribution. This is the website. It's kind of security oriented and also very lightweight. Very, very, really. It's very common to use Alpine to build containers because of this. It uses Muscle instead of glibc. It uses BusyBox instead of the standalone tools. So that's why it's very kind of lightweight. So here I'm building a container with Alpine. So I'm building from Alpine. Alpine is my base image. I'm also building for ARM64, as you can see here. This will actually create a container for this architecture. So behind scenes, Docker will cross-compile everything for me. It would run in an emulated environment. That's very interesting. So I'm taking the Alpine container for ARM64. Inside of it, I'm installing two packages, lighttpd and lighttpd mod out. Then I'm copying the files inside the container, and I'm configuring the command to run the container. Let's build this container now. So the idea here is that we want to build this container and run it in the device. Not sure if I already built this, so I'm gonna prune the container images in my machine -a-f. Okay, we're good. So now we're gonna build this container, a Docker build. I have the command here already. So Docker build, this is the tag. I'm tagging the container with my username, Sergio Prado, the name of the container, that is web app, and the version is 1.0. Dot means use the Docker file inside this directory. And now Docker will build the container for me. Should be very fast, done, because it's a small container. Now, I want to push this container to the registry. So I have an account in Docker Hub. I can log into this account with the command docker login. Actually, I already logged in, so that's why I didn't need to type any credentials. Now I can just push to my account. Should take a few seconds, then, all right, done. So now the container is on my Docker Hub account. Now I can just run it in the device. So I'll go to the device and run the container. This is the command that I'm going to use to run the container. So I'm going to run it and then I will explain why it is running. But it should be fast to pull this container because it is much smaller than the Nginx one, because I'm using Alpine here. So Docker run --rm. This is to remove the container after it has finished its execution. Run it in the background. The name will be web app. I map port 80, and that's actually what caused the problem here, because I already have a container running with this port and I cannot have two. So I'm going to stop the web server container, and then I'm going to run it again. It has already pulled the container, so it should be fast now. Now we have here the mount option and then a big parameter. So here we are asking Docker to bind mount, to mount this file inside the container. This is the file that the CGI script will use to turn on and off the LED. So this is the LED file. And we are mapping it inside the container. By default, it cannot see, it cannot access devices. So here we are mapping this device inside the container. We are bind mounting, the source is this file and the destination is the same file. Then my username, Sergio Prado, the container web app 1.0. All right, it is running. So now I can go to the web server, that should be here, F5. All right. So now it is running. I can turn LEDs on and off. Not sure if you can see it because the LED is very small. Let me see if I can do something here. So it's actually, let me see where is the LED here. Oh yeah, it's here. So off, on. All right, now we can control LEDs from a web server running inside a container in the device. We didn't need to rebuild the distribution, the operating system, include libraries, include web servers, include anything. So anyone could do this, right? If you have a container engine in a Linux device, you can just run anything you want. Last but not least, as I promised you, let's run Doom in the device. So there is this project here called Doom in Docker. It is basically a containerized Doom application using Node.js. Let's run it. So I'm gonna do this from scratch. I have it already here. Let me remove it. Let me show you the whole process. So I will clone this repository, git clone. And then as you can see, this is basically a repository that has a Docker file to build a container with this application, right? So we're gonna build it. Build. This is the command that I'm gonna use to build, docker build -t. So I'm gonna build tagging with my user. The name of the container will be Doom version 1.0. And here I'm passing the platform. So Docker will build this container for ARM64. That's the architecture of the BeaglePlay. Building the container, I can show you the Docker file in a few seconds. So build it. Now I'm gonna push this container to my Docker Hub account. All right. And now we should be able to run this container. So it basically run Doom in a web server using Node.js. So you just need to map port for that. If you look at the documentation, it says that it uses this port 8080. So that's why I'm mapping a different port here. So Docker run, remove the container after it exits execution, then run the background, the name will be Doom, map this port, and run this container. That's it. It will pull the container now. It might take a few seconds. While it is pulling, we might want to have a look at the Docker file. It's very simple. It builds using the Node container. So there is a container with Node and everything that you need to run Node applications. And then it sets the app directory as its working directory, copy a few files to run npm install to install the Node packages. And then it sets the command with npm start. So it's a Node application packaged inside the container. It's still extracting the container. It's not a very big container, but yeah, it's bigger than the Alpine container. Containers can be very small, like as small as 500 kilobytes of disk. You can really create very small containers, or they can be very, very big. It really depends on how you design your Docker file, for example. So you don't need to care about this. I mean, when you are designing a containerized application, you really have control over the content of the container, and you should really care about this. So you don't overuse storage, for example. I guess it is finishing, pulling the container. All right, now it is running our Doom container. Let's wait for the terminal to make sure that the container is running. All right, it started the container now. We can see the hash of the container that it is running. Docker PS. This is a nice thing because now we have two containers running, right? We have the web app and the Doom. Both are web servers, but they don't conflict with each other because they are running inside containers that are isolated from the rest of the system. And I can still access the web app container. Of course, they are using different ports. So if I point here to port 8080, then we have Doom. So now I can play Doom. Inferno. All right. New game. Hurt me plenty. Okay. And then I think I should with this. Yeah. Not good at Doom. I mean, don't play much of FPS games, but yeah, very nice. With a few comments, we were able to build a Docker container with Doom and package it inside the container and run it in the device. All right. And what is nice is that you can take this container and run everywhere on any supported hardware. That's really the beauty of containers. I don't want to say here that you should use container everywhere, but it's really a nice technology. When you have a new project, really think about it. It might really help you increasing the productivity of a development team, right? Think about advantages and disadvantages and try to find out if it really fits your need. I'm seeing more and more people using containers on embedded design. So it's really something that if you are not using right now, you would probably be using soon. I hope you enjoyed this video. I will leave some comments in the description of the video. And if you want more videos like this, don't forget to click the like button and subscribe to the channel. Feel free also to leave a comment in the video. Leave your questions, comments, suggestions, if you have any. And yeah, that's it for today. Until next time, bye-bye.